I built a rover with 3D printed parts, custom software, self-developed gears, and an omnidirectional steering system. In this video, I'm going to show you how I built this thing from the ground up, and of course how it performs in the end. Later in the video, I'll be using planetary gears, installing motors for both the drive and the steering, and finally connecting everything together, so I can test the first driving maneuvers. The goal of this video is to develop a rover AI platform that can be later expanded with a wide variety of tools. In this project, I'm first going to focus on the base, the structure of the rover. After that, the drive and the steering will follow, and various electronic components that connect everything together. Finally, I'll write some software to control and test the rover. Starting with the frame, the structure of the rover, I ordered various aluminum profiles. These are standard materials that are used everywhere in the industry. The outer frame is about 80 centimeters long and 60 centimeters wide. The profiles are complemented by so-called hammer nuts, which keep all the parts perfectly in place. I've added additional connections here so that I can later mount tools or even the steering everywhere. Here's a quick comparison to the first version, which definitely would have collapsed under my weight. The new frame is slightly larger and significantly more stable. Next, I'll take care of the drive and steering for the 4 axles. For this, I will be using my own custom-developed planetary gears. They consist of a ring gear, which is essentially an outer casing with internal teeth. Inside the ring gear, carriers with the planets will be placed later on. In my case, I will combine 2 carriers, each with a ratio of 1:7, resulting in a total ratio of 1:49. The finished components can then be placed into the ring gear just like this. The last important part of the planetary gear is the sun gear, which I use here as the input for the gear system, and which will later be turned by the motor. For each axle of the rover, I will later need 2 gear systems, one of which will be installed in the wheel, just like this. The tire tread is printed from TPU so that it can drive well on any surface. Another TPU printed part serves as a seal between the gear system and the motor housing. Here I am now, halfway through, with 4 finished wheels, and I'm starting on the steering. For that, I first extend the output of the gearbox. This extended output directs the weight that presses down on the gearbox onto the outer casing, rather than onto the internal gears. On top of that, I attach another connector mount with dimensions of 40 millimeters by 40 millimeters, in order to either accommodate standard aluminum profiles, like those from the rover's aluminum structure, or, as in this case, another 40 by 40 3D printed part of the wheel. After about 300 hours of printing time, I then had 4 completed steering and drive systems. Now it's time to move on to the electronic control of the individual components and their monitoring. In order to always know how the wheels are currently aligned, I need to measure this somehow. For that, I will use these small magnetic sensors. This sensor can precisely measure the position of the magnet. The magnet is polarized as described above on the top right, and depending on how the north and south poles are aligned, the sensor knows how the magnet is currently rotating. If I now attach the magnet to the motor's output shaft, I can accurately measure the rotation of the motor shaft. This is what the wired position control system of the motor looks like. The sensors are connected to a Raspberry Pi via a multiplexer. This is needed because all the sensors share the same address, which is a problem when connecting more than one. The multiplexer gives them a unique address. Currently, I have the electronics installed. As you can see here, on the left, the encoders for all the motors to control them. Above that, the power supply to provide electricity for everything. Further to the right, the multiplexer that connects all the sensors for position monitoring. And finally, at the bottom right, a Raspberry Pi, which is currently being used for control and software. Speaking of the software for controlling and conducting the initial tests of the rover, I have written 3 ROS2 nodes. ROS2 is a robot operating system that provides a fundamental structure for how code is written and how different pieces of software can interact with each other. In my case, there are 2 publishers, both of which pass information on to a topic called X or a topic called Y. Another piece of software, more precisely a ROS2 node, can then subscribe to these topics and will receive the information that is being published to them. Other nodes could also subscribe to these topics and receive the same information. The input publisher is used to monitor keyboard input. That means whenever I press a key, a command is sent to the topic. The ASM publisher monitors the position encoders, determines the exact position of the wheels, and sends that data to the topic. The drivetrain server processes all the information and then decides which driving maneuvers should be executed. With that, we can now carry out the first outdoor driving tests. For example, when I press the Z key, the standby command is sent and the rover stops driving. Next, I send the turn on the spot command. First, the axles are adjusted into the correct position, and then the rover starts rotating in place. Here we see the data from the ASM publisher, which currently shows a 45-degree angle. Now, if I want to drive straight again and send the corresponding command, we can see here how the angles gradually change, and also, over here, how they do so in real life. They approach a value of 0 with a bit of tolerance that I'm still testing at the moment. I also wanted to test the overall stability of the rover, so I just sat on it to see if it could still drive straight with the extra weight. It's not super fast, but that's not really the goal. It's just about moving forward with enough power. The steering mechanism also seems to handle the extra weight just fine. Next, I wanted to get a rough idea of the pulling power, so I just held on to it to see if it could pull me. That worked without any problems too. After that, I grabbed my force gauge to get a more precise measurement. I reached a peak of around 18 kilograms before the front wheels began to lift off the ground. If I added more weight to the front of the rover, I'd probably be able to measure significantly higher values as well. Next, I'll be adding a few more driving modes, like adjusting the course while driving and drifting sideways. Then, I want to increase the intelligence so that the rover can act independently. That's coming up in the next videos, so stay tuned and subscribe to the channel.